Thank you, Anna. I'm very glad to have this opportunity. Quick correction, most of this is actually about the research leading up to that point. It's actually not going to be about the company. But you will quickly know why I call myself a pseudo data scientist. I was not trained in data science. My background is communication networks, bit of applied probability, stochastic control. I worked many years on sequential decision theory, online learning theory, resource allocation, most of them within the context of wireless networks in a very resource-constrained setting. So we look into incentive mechanisms between multiple competing users, very, very different from data science. As a matter of fact, most of what we did was writing proofs of theorems. And if you've done that, you know there, the important thing is to make up right assumptions, good assumptions, so you can go through with the proof. And most of the work didn't actually need data to back it up. We have to justify proofs of the assumptions, of course. And so what's implied in this background is not only that I wasn't trained in data science, but I was not an expert in cybersecurity either. So how did I get into this? This is something that I ventured into about 4 years ago. And as you will see, up to this point, we've been using a fairly basic, I would say, first-year graduate student level machine learning tools. But I hope to show you what are the innovative aspects through this exercise. And this exercise has actually also opened up other research avenues for me, and that is in the space of policy design, which I actually have always been very, very interested in. So how did I get into data? Well, through collaborators. I was working with computer scientists who specialized in internet measurement. And this is a very vibrant research community in computer science. But what they tend to do is, internet is huge. The focus oftentimes is how to get the data. And so the drive for getting the data often outpaces the thinking behind what do we do with the data once we get it. And so the analysis tends to be very elementary. And because I was doing a lot of modeling work, and by the way, I should have said at the outset, the reason I wanted to talk about this is I think as a researcher, every time we get into a new area, what we have to go through is very, very similar to what a first-year graduate student is experiencing. You will see there are a lot of setbacks and frustrations, desperation, and so hopefully the experience is helpful to at least some of you, right? So here are two examples of data sets they came to me with, and because of my background in modeling, they were hoping maybe we can do something slightly more sophisticated with the data. The first set of data is what's called reputation blacklists, RBLs. You may not have heard of it, but you are all personally affected by it. Two ways. One is occasionally you may have had the experience that when you try to send an email, you get an automatically bounced back message saying your message cannot be delivered because your IP address has been blacklisted. If you haven't had the experience, good for you. I have. So what these lists are, so they're these organizations and research groups who deploy monitors and sensors throughout the internet, trying to filter traffic. And by examining the traffic, they try to detect whether the traffic is malicious. For instance, whether the packet is part of a spam email, whether somebody is scanning illegally, okay, other IP addresses, whether an IP address is running a phishing site. And once they did make these detections, they compose a list of IP addresses from which this traffic was coming from. These are source IP addresses. So these are basically blacklisted IP addresses. They compose these daily lists, and these lists you can subscribe to. Some of them are open. And almost all your inboxes are filtered based on some type of access to these blacklists. Okay? This is in addition to the local version of spam detections and so on. okay? So this is one type of data. What it has is just millions and millions of IP addresses that have seen to send, engage in some type of malicious activity. Second type of example that they came to me with is service or network configuration issues. I'll give you a very good example. Your department, doesn't matter which department you're from, it's very likely somewhere in your department there sits a printer that is visible halfway across the road by an attacker who can see it, meaning that he can ping it. The IP address is openly accessible. It's also quite likely that that printer has never been configured to have a new password, meaning the password is the default manufacturing password. So people with knowledge can log into that and do things with it. Now, as a printer, maybe the most they could do is just print out junk that you may not like. This is very common. There are more serious configuration issues that advanced measurement techniques can try to detect. What you glean from this type of data is deviation from known best practices. We know the best way to configure, to lock down the service is such and such, but they're not being followed, okay? So the question is, what do you do with them? What we wanted to do was something that is quite different from what others have done. So typically what people are doing with these is they basically they look at first order, second order statistics, they look at the trend, the global trend over the past few years and make some observations about it. We asked the question, can we take this type of data and maybe many others of similar types and try to quantify the overall security posture of a block of hosts, IP addresses, a network, or an organization. And the reason we're interested in this is we want to be able to see whether there are high-level policy issues that this can enable us to design. And I'll come back to this. So then the associated question is, if this is what we want to do, then we need to ensure that the metrics that we come up with to quantify the security posture can be justified. And if this is possible, then what we can build is a global security rating system, reputation system, okay? That very much parallels consumer individual level credit rating system. Why do we think this was a good idea? There are myriad threats to internet security and availability. I need not go into this. The cyber threats are now such a daily occurrence, we're all quite familiar with them. If you look at the landscape of defensive strategies, there are plenty, but most of them are focused on hosts, individual hosts. Blacklisting IP addresses, one thing I just mentioned. And there are a lot of solutions that engineers have come up with that are installed on individual hosts. For instance, intrusion detection systems, software patching, and so on. All these are very useful. But we were thinking something that's orthogonal to this or complementary to this. The other thing that comes with host-based solutions is they're heavily detection-based. Okay? Essentially, you have to wait for the problem to occur, and that's the case with the intrusion detection. That's also the case with filtering blocking systems. Okay? And a lot of times, by the time a problem has occurred, then you're in the damage control mode. The damage is already being done. Our vision is, again, is rather orthogonal to this and complementary to this. We want to assess the network as a whole, not as individual hosts. And underlying this is our belief that a network is typically governed by consistent policies. And what's behind policies are people. Now, systems change, operating systems change, patches change. The human resource behind that's running the system actually changes at a much slower time scale compared to this. And the resource and the expertise, similarly, they change on a larger time scale. The consistency leads to predictability. And consistent doesn't mean it's static, it can be dynamic. And predictability is what gives us the ability to adopt more proactive policies. So from a policy perspective, this opens up, if we could do this, then it opens up new avenues. The other thing is that a lot of mechanisms, incentive mechanisms in particular, can only be applied at a higher level and not at the host level, okay? So for instance, a very common semi-incentive mechanism is cyber insurance, okay? As both a risk mitigation and a risk reduction mechanism, you cannot write policies for individual hosts. That has to be written for an entire organization. So you want to incentivize the right policy making, the right resource allocation decisions at a high level, okay? Because a lot of, as I will point to, a lot of cybersecurity problems are ultimately people problems. People who don't have the right expertise, who don't have the right mentality, who do not follow their due diligence. A lot of these the major breaches, they all really originate from very, very elementary issues, right? We had the right vision, but we had many, many failed attempts. One of the root causes of this is, well, we want to define metrics to summarize, to quantify security posture of an organization. In defining these metrics, and because we're looking at very different data types, they're capturing different aspects of the organization, defining these metrics can appear arbitrary. There are so many different ways to do this. Temporal analysis, unsupervised learning, I can try to build synthetic models. And that often runs into the problem of how to convince people, say reviewers, whenever you present this work to funding agency, to peer reviewers, is why is one way better than the other? And ultimately, what can we do with it? Okay? The typical response, I would say, is the shrug of the shoulder and so what? Yeah, sure, interesting. We tried many, many things. We tried correlating different posture measurements with geographic locations, with different types of organizations. They're interesting observations, but at the end of the day, oftentimes what we got was, so what? So I will not tell you how many times we tried to submit this type of work. My students were getting very, very desperate. So we did this, and every time I think we were making a little bit more progress. But we were stuck on this probably for a good 2 years. And the issue is, how do we convince people that this is useful? Eventually, we had an idea. And the idea came from another source, which is by then, I think this was 2014, 2015, you start hearing more and more about high-profile data breaches, okay? I'm sure each of you can name a few. This was 2014, Target, JP Morgan Chase, Home Depot, Anthem, and I'm sure many of you here probably have received letters to the effect that your data may have been exposed. As a compensation, we offer you 1 year free access to your credit reports. I got this from my alma mater, University of Maryland, twice. And the increasing social and economic impact of these cyber incidents are obvious. Okay? The data suggests that between 2010 to 2014, 95% increase in the average cost of these. As these were being reported more widely and consistently, the idea came to our mind, which is, can we use these breach reports as labels to enable supervised learning? I'm talking about standard supervised learning. what we had, these data we have, anything we did, we're essentially extracting features. And unsupervised learning that we were doing over these features were considered unconvincing, okay? Even though we had interesting observations. So the next idea was, let's use these breach reports as labels, okay? So we can build classifiers that can actually then predict data breaches, okay? And in the process, we can use many of the metrics we developed earlier that we consider useful as features in the training of the classifier. So that was the idea we had. Now, in hindsight, I think a lot of peer researchers I talk to will say, yeah, that's such a natural thing to do. But when you were going through this process, it was not at all a natural thought. And that's because the breach report is a very different beast. It is primarily collected by law enforcement agencies and reported by news media. It's a very different source, and it requires very different collection methodology compared to internet measurement data. And it's also a very, very nascent field in the sense that different breach disclosure laws are being enacted at the state level. California, for instance, has perhaps one of the strongest consumer protection, data protection laws. So you see very uneven disclosure rates from place to place. There lacked and still lacks a standard, consistent standard for reporting. So if you look at some of these reports, people use very, very different languages, perhaps to mean exactly the same thing, or the same language, perhaps to mean very different things. There's no uniformity in that. And so the noise level and the incompleteness of the set of data was basically a major hindrance, so you don't often consider this as a data source. Verizon was indeed starting to collect such data and analyze the year-on-year trend. And turns out, in order to collect this data, they go to local law enforcement agencies, they crawl attorney general's websites, and it was just a large amount of FOIA requests that they filed with the courts to get the paperwork. But once we decided this is what we could do, we're going to try this, then it actually significantly augments the application we originally had in mind. If we can do breach prediction, then it is extremely useful in enterprise risk management, because if I know my risk lies, it can help me make decisions in prioritizing resources and take proactive actions. It is also very helpful in third-party and vendor validation. Large companies typically has a list of thousands and thousands of potential vendors. The typical decision regarding which vendor you choose, University of Michigan, for instance, our mail service, our file storage, have all been outsourced. These are all U of M vendors. When you decide which vendor to use, Google versus somebody else, what factors do you consider in making that decision? What we are arguing here is cybersecurity posture ought to be one of the factors when you make that decision. If you look at breaches like Home Depot and JP Morgan Chase, the breach was all brought on by a third party, okay, a vendor. And last but not least, if you can do this type of risk assessment, you can design better incentive mechanisms, going back to the example of cyber insurance policies. That would be the first time that you can actually write a cyber insurance policy with something close to actuarial information, which they have in other mature products, but they don't have in cybersecurity, and yet they write large quantities of insurance policies to the tune of billions of dollars in premium. I've actually seen U of M's own insurance policy, and it's very interesting. It's something, if you're interested, I'd be happy to talk more offline. So the next few slides, I'll present to you the breach prediction framework we eventually built. What we wanted to do was we want this framework to be scalable, meaning that we don't want to have to knock on everybody's door and get their internal data in order to do this. So we rely completely on externally observed data. And that fits well with the example data sets that I presented earlier. We also wanted the framework to be robust because we know very, very well each data source we have can be very noisy, and we don't always have control over or even the knowledge of what that error is and the origin. And last but not least, a lot of these data that we have to work with, they're grossly incomplete. So what we relied on was to use as much different types of data as possible. And the hope is that the error sources are different from different sources so that they have a compensating effect. When you put them all together, this is one thought. The other thought is in order to do this type of risk prediction, we wanted the data to capture very different aspects of an organization. It's not just the explicit signs of infection, okay? Botnet infection, your machine is sending out spam. We also wanted to capture latent signals. And one example is the misconfiguration and mismanagement that I was referring to earlier, because that gives you a very, very good sign of how competent the people are who are running the network. It can be very hard to convince IT people that those data types are useful because they'll argue, so what if my printer is left open? Or my valuable data is locked in a lockbox? I've heard this many times. But what is that telling you? What that tells you is if you don't have the paranoia or the sense that if the printer doesn't need to be open, you have to lock it down. Okay, it's the other way around. It's not that I don't see harm and therefore I'll leave it open. No, no, no. If it doesn't need to be open, you lock it down. If you don't have the training and the mentality to do that, then that casts doubts on how well you're doing the lockup job. And you see from our exercise that oftentimes is very true, is that you can't just think, I've locked my valuable things in a safe. We don't know how well you're doing that. And there's a great correlation between these other things you're doing that seem benign to the more crucial things that you're doing, and maybe we don't have direct observation of. Here's, in this prototype study that I'm going to show you, I use exactly the same two types of data that I presented a few slides ago. Malicious activity data, we sourced this from 11 different blacklists. They capture generally 3 different types of malicious activity: spamming, phishing malware, and scanning. And we also use a large quantities of mismanagement symptoms. One good example here is HTTPS certificates. This you probably all have had experience. You're trying to visit some sites and your browser pops up message saying, do you really want to go there? The site doesn't have a signed and valid certificate. Okay? That's usually a sign that, well, either it's an illegitimate site, okay? Maybe it's a phishing site, it's a proper warning, but oftentimes it is a legitimate site. It's safe to go, but they have a certificate that's either not signed by a certified authority, certificate authority, or it has expired. This happens all the time. They let them expire, they don't renew it. Again, you know, a lot of people argue, so what? What's harm? I let it relapse for 2 months. Well, it's a sign that you perhaps the organization doesn't have enough human resource to stay on top of these things. And what does that tell you about other things they're doing? Okay. And then we source from different places the incident data sets that we use as labels. Again, this is a quick illustration of how non-uniform incident reporting is. If you look at these data sources, they use very different categorization of the incident types. In this particular exercise, we basically lump them all into a label of one, whether there is an incident or there isn't an incident. But this gives us a lot of headache when we try to do type prediction. All right, so basically we then used the first two data sets to extract features and the last one to use as labels. 90% of our time, my students and my time, ends up being cleaning the data. It was, the data is, the biggest problem we had here was our mismanagement data and our malicious activity data, they come at very different resolutions, okay? One is associated with they both are associated with IP addresses, but our label data, breach reporting is associated with an organization, not a single IP address. So you have to do a lot of work to map them. And the mapping process is manual labor intensive because it's not readily available. You have to go into these routing information registry databases and try to do a lot of the matches. Essentially, query and verification, re-verification by hand. So it ends up being a very labor-intensive process. Does it work? So here I'm showing you an example. So you train your classifier. Here I'm showing two distribution curves, one of a non-victim set, the blue curve. The other is a victim set, the red curve. The large difference and the distribution is over the classifier output. It's a number between 0 and 1. The large difference immediately shows you that it contains information. And here I'm putting on the map major breaches, publicly disclosed breaches in 2015. And this was run using pre-breach data. So what you see is all these hypothetically could have been predicted as being high risk. The one at the top is Penn State. I didn't put U of M here, it's not good. Universities tend to be bad because we run our networks from an open principle, so a lot of things can happen. Overall, just to summarize, we can very comfortably achieve, this is across different label data sets, roughly speaking, 90% true positive and 10% false positive. Okay? So it's pretty good performance. We did one more thing, which is fine-grained prediction. This is now, what if I ask the question, not only what my overall risk is, but can you predict what type of incident I'm going to have? Okay? It's a similar principle, but much harder to do because the breach reports are so incomplete, as I showed you earlier. The categorizations vary, and one report will say a physical event, but it doesn't say whether it's a physical theft or physical other events, okay? So we had to use additional data inputs. One of them is web traffic statistics from AWS, and do a lot of tweaking of standard models to compensate for incomplete models. Essentially, we have to do the risk estimate piece by piece, using the maximum number of labels we can use, not counting on complete labels. But here's a quick illustration of what you can do with this type of risk estimate. Here, information and public administration are two industry categories. You can do essentially the estimate for two broad industries, and I list two examples within each industry. What you see here is when you do this type of exercise, then they're catered to the specific organization you're examining. Their profiles can look very, very different from their relative industry. Verizon here, for instance, compared to its industry information, is much more across-the-board risky. Now, that could be a sign that Verizon, as a large company, is prone to report everything that's ever happened to it. Whereas here, public administration as a sector is across-the-board risky, but Internal Revenue Service is really just risky to two things, error and misuse. And the crosses here are what actually happened to that organization. So this is an illustration of how you can do very, very targeted risk estimate. So with these things we have done, we finally had enough to convince people that this is useful. We were able to publish a few papers. My students were very, very relieved when we had the Usenix security paper accepted. You know, sometimes it comes as a surprise to advisor because my word doesn't actually count as much as the reviewer's words. When you receive rejection again and again, you have a lot of doubt. I'm not sure what you say is correct. This is what other people are saying. And it was also well received by peer researchers and funding agencies. And surprisingly, we had commercial success, as I just mentioned, because I was trained mostly as a pen and paper researcher, proving theorems and all. I never actually imagined I would have a company. But once we did this, the commercial application behind it became so compelling, we did it. And it happened really fast. We did it in late 2014. We were featured in a Wall Street Journal article in January 2016. And we also named Gartner Co-Vendor that year. And we were acquired in May 2016 by FICO. Who's FICO? FICO is the one giving you the score on your credit card statements. Consumer ratings agency. And so what we're building here is being recognized by them as a parallel to their consumer, basically enterprise security ratings system, paralleling their FICO score. So a few thoughts. I'm almost done. Again, as essentially somewhat of an outsider to data science, what I see is it's an uneven landscape in how data is used in different fields. I think some fields are truly big data that require very advanced tools to be scalable, performance, efficiency, and so on. But there are also other fields where people spend years and years to get data, which have now outpaced the thinking behind to drive its use. So there basically are areas that have just become data rich but need creative ideas on what to do with the data. I think cybersecurity is becoming like that. Not everybody will agree with my assessment, but I think it's a good time to apply data analytics to make new contributions. There's abundance of data. You will need some domain expertise, but there's a lot of opportunity there. And I also firmly believe good analysis can inform policy design and opening up new areas. If you're interested in data analytics and machine learning tools, this is probably mostly, I like to say this to our own ECE students, because I see this among my own students. They don't always embrace data. They realize, man, most of my time is scrubbing the floor. When do I get to dance on it? You don't. Almost once you're done cleaning there, it becomes obvious. Some students learn to embrace it. Some don't. Some will stay sort of on the sideline and try to do as little as possible or just enough so they can run their algorithm on it. I think this is a good case study to highlight some real challenges and different aspects of it. But if you do come out the other end, I think the results can be very rewarding. And embrace what comes your way. Thank you. I should acknowledge my students.
Model emotional information, which makes sense. We know that people need context to be able to interpret behavior. But what we also find is that we can pretty accurately characterize emotion using 3 different things. One, short time pieces of information. So just